the two. There's a lot of base, there can't be a lot of acid. You get this number here, extremely small number. Second thing to keep in mind, you take the negative log of a value. The negative log, your exponent here is to the minus 12th power. Your value that you're going to get out for your pH is going to be close to 11.85. I'm sorry, close to 12, it's 11.85. Those two numbers articulate back and forth. They'll be off a little bit because it would only be 12, exactly 12 if this is 1.0, but it's 1.4. But it does give you a handle. This amount here is very small. It's to the minus 12. Tells you your pH is going to be somewhere around that same order of magnitude, somewhere around 12. Looking at that pH on our scale, we can see pH at 11.85 means there's basically no acid there. There's a lot of base. Try to measure something that's a minus 12th power. It's very difficult. There's none of it there. Okay.
Would it matter which way you went? Because the way I did it, I was just diddling, practicing. I did the POH and I subtracted from 14. I gave it pH.
Another way to do it. Absolutely. That's it. The way you did it was you took this. You took.
I took the negative log of POH and then subtracted 14.
That works the same way. Yep, more than one way around the block. Ask you, and they'll sometimes do this, and I'm going to show you a different way to do it than what you see in the book. Nothing wrong with the way the book does it, however, this way is a little bit more straightforward. It says calculate the hydroxide ion, the hydronium ion. Calculate H3O plus concentration when the pH is equal to 8.37. Your book walks through, and you can see it, the examples there. This is in 15.4. But I think it's easier than to do this equation. This equation says 10 to the minus pH equals the hydronium ion concentration. Your book does it by using an original equation and then resolving it. It's a lot easier to me to just use this equation. This equation says whatever the pH value is, raise it to the 10x power, and we'll get the hydronium ion concentration. So in this one, in this example, we have 10 to the minus, pH was 8.37, 10 to the minus 8.37 equals H3O plus. This is your 10x button, so you're going to put in 8.37 negative, raise it to the 10x, your hydronium ion concentration is 4 times 10 to the minus 9. Your book walks it through using the pH equation and then solving it. What they do is essentially come to that same equation. Your book doesn't, in words, show that equation. You'll have that equation when it comes time to do a test. I think it's a much easier way to solve it. One other one that goes with it. Put a bracket around that one. That's another one that gets you between pH and pOH. Like I said, if you look in the book, the way they do it is slightly different. It's just as easy to have the expression and be able to balance between H3O plus and OH minus. When we look at these types of guys, we want to be able to find the pH of a solution. And this is where the equilibrium part comes back again. When we look at acids and they ask us to find pH, there are really two different cases, and the discussion starts with the strong versus the weak acids. Back to those again. The strong ones, easy to deal with because everything breaks apart. The weak ones become the equilibrium problems, just like we saw in chapter 14. Let's take a look at where the dividing line occurs. Let's look at a strong acid case. This will be finding pH. First one's strong acids. Strong acids are the easiest ones to deal with. There's nothing we have to really worry about with strong acids. For example, because they break apart 100%, we can use whatever the strength is that is told to us and find the relationship directly. Example. If you have 1.0 molar hydrochloric acid, they tell you that's what you're starting with. We can assume that all of that acid produces hydronium ion. Because it's a strong acid, we can say that the H3O plus concentration is also 1.0 molar. Because all of it, all the H's in the HCl are going to be released. And so the concentration of those is directly the same. It only works for the 6 strong acids that we talked about. That's it. So if we needed to find the pH of that, it's pretty straightforward. The pH, negative log, hydronium ion concentration, which is 1 molar, is your pH of 0. There's nothing we have to do with these because we can use the concentration directly because all of it breaks down. That's only 6 acids. All the weak ones we have to worry about, well, how much of it's breaking down and to what extent we have to do the equilibrium calculation. Let's contrast that with example 15.5, which says the following. Strong acid, easy. Weak acid. Remember when we talked about equilibrium last week, we said it's always worth a shot to see if the assumption will work. That will stand in this chapter just as it did last week. Always take a look at the data and see if you can take a run at doing the problem without the quadratic. There are times you'll have to, there's times there's nothing we do about it. A lot of times with these, you'll find out that you can get around the quadratic pretty quickly. Let me show you an example 15.5. Example 15.5 says find the H3O plus concentration for 0.25 molar HF. When you start to see these problems, a couple things to remember. First, write a reaction. Just a base sketch of what the reaction looks like. So, we know that HF plus water we have that. The other thing we can take a look at is, since we're dealing with this, look to see if it's a weak acid. Because in the first two of the problem, you're not going to know if it's weak acid or not. So look for a Ka. If you try to look up a Ka for hydrochloric acid, it's not on the list. Why? It's a strong acid. It doesn't have it, so it tells you which way the problem's going to go. HF. Look up the Ka for HF in the table. When you do so, 3.5 times 10 to the minus 4. So get used to write a reaction, 2, look up the Ka value. Next thing that we can do.
We get the list. We can get the list of the Ka. But well, I mean, for our test, since we can't use the book.
Oh, absolutely, yeah. There are 2 ways. Usually, what happens on the test, I'll tuck them right in the problems.
Okay.
Or the other option I can do is just give you the whole table back. But it's usually easier to just put it in the problem.
Are you also going to use the quadratic?
Oh yeah. The x equals plus or minus. Yeah. Yeah, I'm not expecting you to remember that. Next thing we have to do is look at what's happening here. We have to set up an ice table. Let's write our reaction again. HF plus water goes to this. That. There's our reaction. The initial change equilibrium. They tell us we're starting with a quarter molar, 0.25 molar HF. 0.25. We know, other than the lab you did the other week, we don't worry about the water. Water's dropped out of the expression. We assume that if they're putting this into solution, that none of the acid or its anion were present at the start. They don't tell us anything about it, so we assume it's not present. That's all they tell us. So everything else here becomes X. This, because it's on the reactant side, is going to lose some amount of the material. These two are going to gain some amount. We can write our equilibrium amount, 0.25 minus X, X, X. We wrote the reaction, looked up the value, wrote the ice table. Next thing is write what the Ka stands for. We know what it is numerically. We know that the Ka in this case is 3.5 to the -4. We also know that 3.5 times 10 to the -4 equals the product over the reactants. Well, we have H3O plus. We have F minus. We have HF on this bottom. That's our standard part. We know what it equals now. We can now substitute in what we know at equilibrium. At equilibrium, we have that. And we sit now at the cusp of deciding, do we go the quadratic route or do we take a shot at the assumption? The -4 sits right on the barrier. -5 would be better. That's a fairly concentrated solution of 0.25 molar. So I'm going to say, try the assumption. In doing so, I'm going to say that this number, this minus X here, is negligible. It's not going to break down a lot, so this minus X isn't really going to be a factor. So I can rewrite X times X is X squared over 0.25. I'm saying that's not going to change enough to affect the final number. Pretty easy to find X squared there. I can find X squared by taking to find X, I'll multiply those two and then take the square root of the value. In this case, X works out to be 9.35 times 10 to the -3rd. That is in moles per liter. So we got a number, and the question is the assumption valid? Did I do a reasonable job at finding out whether that assumption works? In order to validate that, we have to check if it's under 5%. 5. I'm going to validate it. If I take 9.35, that was 10 to the -3rd, compare it to the 0.25 that started, how much it came with, times 100%, that numerically works out to be 3.74%.